Hello everyone, I am Dr. Munish Kumar Bharadwaj from School of Engineering and Technology of IGNOU. Today we will discuss test on aggregates. In this lecture, we will cover flakiness index, elongation index, sieve analysis, fineness modulus and grading of aggregate. So let us begin with first flakiness index and elongation index. Flakiness index. What is flakiness index? Aggregates is termed as flaky when its least dimension, that is the thickness, is reasonably small related to its other two dimensions. Other two dimensions means width and the length. The amount of flakiness is denoted by the flakiness index. So you understood this meaning that an aggregate will be termed as flaky when its least dimension is reasonably small relative to its other two dimensions. So this flakiness index is given as the percentage by weight of particles in the sample of aggregate whose least dimension is less than 3/5 of the mean dimension. Mean dimension means the mean sieve size fraction to which the particle belongs. Means we will do the 3/5 of the mean dimension, and this flakiness index will be given as the percentage by weight of the particles in the sample of the aggregate whose least dimension is less than this dimension, 3/5 of the mean dimension. Then for example, we have aggregate sample of 20 mm mean size. Then any particle of this sample of thickness less than 12 mm. How we reach at 12 mm? That we will do the 3/5 into 20 mm, because we are taking the 20 mm mean size aggregate. So 3/5 into 20 means that 12 mm. So will be designated as flaky aggregate. It is measured with the help of the standard metal thickness gauge, and it is described in IS 2386 Part 1 1963 code. The thickness gauge has aperture of different sizes. There is a gauge basically, and it is having different size apertures. A sample of aggregate is taken and sieved through a set of sieves ranging from 63 mm to 6.3 mm, and particles of each fraction are collected separately. Means we will be sieving that sample through a set of sieves. There are number of sieves ranging from 63 mm size to the 6.3 mm, and after doing that sieving, basically the fractions retained on each sieve will be collected separately. The aggregate sample should be taken in sufficient quantity so that each fraction sample should have at least 200 particles. Means the fractions that we will be getting after sieving, so each fraction should have at least 200 particles. So that much of aggregate sample we should take for doing this test. Now particles of each fraction are allowed to pass through the corresponding aperture individually. Means we will be picking these particles individually and we will trying to pass through the particular aperture. Then the flakiness index will be calculated as that flakiness index will be equal to the weight of particles passing through thickness gauge divided by the total weight of the sample into 100. Means the particles which are passing through different apertures, that weight divided by the total weight into 100. Here you see this is the gauge. You see here the different apertures of different sizes. So as per the sieve on which the material is retained, so those particles you will be taking, and accordingly you will be trying to pass through the particular aperture basically, and that number of particles will be collected which are passing through the particular aperture, and that will be weighed. So this is the way to calculate the flakiness index. This is another picture of this gauge. Basically you here see the different apertures that you will try for getting that result. Now the elongation index. Aggregate is termed as elongated when its greatest dimension. Here we are taking the greatest dimension. In flakiness index we were taking the least dimension. Here we are taking the greatest dimension, that is the length basically, is reasonably large relative to its mean dimension. So here the point of focus is the greatest dimension, means the length of the particles. The amount of elongation is denoted by elongation index, and this elongation index is given as the percentage by weight of particles in the sample of aggregate whose greatest dimension, that is the length, is greater than 9 by 5 times of their mean dimension, that is the mean sieve size fraction to which the particle belongs. So here the dimension will be decided based on the 9 by 5 times the mean dimension. For example, if we have aggregate sample of 20 mm mean size, then any particle of this sample having its length greater than 36 mm. How we get this 36 mm? That you will be multiplying that 20 mm, that mean size, by 9 by 5, then we get the 36 mm. So that way any particle having length greater than 36 mm will be designated as elongated aggregate. The elongation index is applicable to particles of size 6.3 mm or greater. It is measured with the help of standard metal length gauge, and it is described in BIS code IS 2386 part 1 1963. The length gauge has apertures of different sizes. A sample of aggregate is taken and sieved through a set of sieves ranging from 63 mm to 6.3 mm, and particles of each fraction are collected separately, as we did in flakiness index case. Now the aggregate sample should be taken in sufficient quantity so that each fraction sample should have at least 200 particles. This precaution we described in case of flakiness index also. Similarly, the particles of each fraction are allowed to pass through the corresponding aperture individually. Here also we will be picking the particles individually and we will try to pass through the corresponding aperture. Now the elongation index is calculated as the elongation index equal to weight of particles on the length gauge divided by the total weight of sample into 100. So that way the number that you will get after calculating this, that will be called as the elongation index of the aggregate. The presence of elongated, blade-shaped or flaky particles both in coarse as well as in fine aggregates should be avoided for concrete. It could be restricted to 15 to 20% by weight of total aggregate for normal concrete. What is the effect basically? The presence of such type of particles adversely affect the strength of concrete as they act as a weak link within the gel structure of the concrete. The surface area to volume ratio for such type of particles is high, which adversely affect the workability of the concrete mix also. Now you see here the length gauge for determining the elongation index. So here different apertures are there in this length gauge, and we try to pass through the individual particles through a particular or corresponding aperture, and then after collecting that the weight of that sample is taken basically to calculate the elongation index. Now let us move to sieve analysis, fineness modulus and grading. Here we will be doing the sieve analysis, and based on that sieve analysis result we will be doing the grading of the aggregate basically. First let us see what is the sieve analysis. Sieve analysis is a procedure for finding the proportion of different standard size fractions of aggregates present in a sample. Means we are finding the different fraction of aggregate present in the sample of different sizes. That is called the sieve analysis. And we are calling this sieve analysis because we are using sieves for this purpose. In this, aggregate sample is sieved through a set of standard sieves arranged in descending order. Descending order means at the top you will be having that sieve of greater size, and accordingly when we go down the sieve size will reduce. So the aggregate sample is sieved through a set of standard sieves arranged in descending order from top to bottom with sieve of maximum size at the top. Here you see in the figure the different sieves. Basically at the top is the larger size, at the bottom is the least size. As per IS 2386 part 1 1963, the sieves used are 80 mm, 40 mm, 20 mm, 10 mm, 4.75 mm, 2.36 mm, 1.18 mm, 600 micron, then 300 micron, then 150 micron. And if you see these different sizes, you will note that the size of any sieve is about half of the previous sieve. As you see, after 80 mm, next is 40 mm. After 40, next is 20 mm. So the next sieve is half of the previous one. For performing the sieve analysis, appropriate weight of aggregate sample is taken as described by IS 2386 part 1 1963, and these are also given in the table 1 that you will see later. The weight of the sample to be taken depends upon the maximum size of the aggregate present substantially in the sample. Here you see this table. Here this gives you the minimum weight of aggregate sample to be taken for sieve analysis. For example, if the maximum size of the aggregate presents substantial proportion in mm is 63 mm, then the minimum weight of the sample to be taken for sieving is 50 kg. Similarly, for 12.5 mm, then weight is 1 kg. So that way, for different minimum size of aggregate substantially present in the sample, different weights, minimum weights are defined in the code basically. Here you see the sieve shaker and the set of sieves. Because sieving is done basically after putting that sample on the top sieve, basically what we do, we put on the sieve shaker, and this sieve shaker shakes the whole set of sieves, and then due to shaking, what happens, the sample passes through different sieve sizes, and finally the lowest particle or the least size particle goes finally to the pan, which is at the bottom of this set of the sieves. After sieving the aggregate sample, let us take that we are taking the 1 kg of the sample through the set of sieves in standard manner. The material retained on each sieve is measured by weight. The weight retained on each sieve represents the size range of particles. For example, weight retained on 2.36 mm sieve indicates that this particular fraction of aggregate is having the particle sizes more than 2.36 and less than 4.75 mm. So this is the meaning. Now here in table 2, you see that the calculation of sieve analysis to determine various related parameters. So the sample taken is here 1 kg or the 1000 grams basically. Sieve sizes, if you see here, IS sieves we are taking 10 mm, 4.75 mm, 2.36 mm, 1.18, then 600 micron, 300 micron, 150 micron, and finally the pan at the bottom. Then weight retained, if the weight retained on different sieves is 30 grams, 120 grams, 150 grams, this is the sample basically, one sample calculation is taken. So weight retained percentage you can calculate by dividing by the total weight of the sample, like 30 grams divided by 1000 into 100, so you'll get that 0.3. Likewise 120 divided by 1000, you'll get 12%. So these are the percentages. In the fourth column, you see the cumulative percentage retained. Cumulative means all that percentages added up to that particular sieve. For example, for 2.36 mm sieve, if you see above it is 0 for 10 mm and 3% for 4.75 mm, and for 2.36 mm it is 12. So you add all these 0 plus 3 plus 12, then it comes out to be 15. So that way all the calculations of the column 4 you can do. And finally the total sum of the column 4 comes out to be 277, means the cumulative percentage retained total for that whole sample is 277. Then cumulative percentage passing you can calculate by subtracting the cumulative percentage retained from 100. 100 minus the cumulative percentage retained, you will get the cumulative percentage passing. So that way the numbers of this column 5 you can get by doing this. Now the percentage weight retained on the any sieve SX, let that sieve size is SX, equal to weight retained on the sieve SX divided by the total weight of the aggregate sample into 100. So that way we can calculate for 2.36 mm sieve, the percentage weight retained on 2.36 mm sieve is 120, because we saw there that 120 gram weight sample was retained on 2.36 mm sieve size. So 120 divided by 1000, because we have taken the 1 kg of sample, so 1000 grams into 100 equal to 12%. So that way you can calculate, as I told you, for the column 4 basically. The cumulative percentage retained on the sieve SX indicates the percentage of particles in that sample of aggregate coarser than sieve size SX. Cumulative percentage passing on each sieve is obtained by subtracting cumulative percentage retained on that sieve from 100, as I told you. So that is the cumulative percentage passing will be equal to 100 minus cumulative percentage retained. The cumulative percentage passing through the sieve SX indicate that this much percentage of particles in that sample of aggregate is finer than sieve size SX. Observations of the sieve analysis are used for drawing the grading curve and defining the grading of the aggregate and for determining the fineness modulus. So for that purpose you can use the result of the sieve analysis. By comparing the results of sieve analysis of fine aggregates with the standard table given in code IS 383/1970, the zone of sand can be identified, and these zones are basically 4 zones: zone 1, zone 2, zone 3, zone 4. Table 3 here gives the grading limits for fine aggregates for different zones. Here you see the IS sieve designation as 10 mm. So for grading zone 1, the percentage passing will be 100%. For grading zone 2, again 100%. For grading zone 3, again 100%. For grading zone 4, 100%. Likewise, if you see for 2.36 mm sieve size, for grading zone 1, the percentage passing is 60 to 95, whereas for zone 2 it is 75 to 100. For zone 3 it is 85 to 100. For zone 4 it is 95 to 100. So this way these grading limits for fine aggregates for percentage passing through the different sieves is defined. So what these different zones indicate? The zone 1 indicates coarse sand and zone 4 represents the fine sand. This information is useful for performing the concrete mix design. It is recommended that use of the fine aggregates conforming to zone 4 should be avoided in reinforced concrete unless the suitability of using such aggregates is ascertained through tests. So this way, this information is important. Now let us move to fineness modulus. The fineness modulus is a numerical index which gives general idea about the coarseness, means the mean size of the aggregate, that how coarse the aggregate is. So it gives an indication of the coarseness of the aggregate. It doesn't provide any information regarding particle size distribution in the sample of aggregate. It is determined by the formula given here, the fineness modulus equal to the sum of the cumulative percentage retained on each sieve divided by 100. So this way we calculate the fineness modulus. Here in this table, you see that based on our sieve analysis results, we can get the fineness modulus for that particular sample. So here you see that for column 4 gives you the cumulative percentage retained, and summation of this column comes out to be 277. So the fineness modulus will be given for this sample as the 277 divided by 100, means it will be 2.77. This is the fineness modulus for that sample that we took for the sieve analysis. Now it can be viewed as weighted average size of a sieve on which particles are retained. This fineness modulus can be viewed like this. The sieve being counted from the finest sieve as 1 and going up, number increasing. So the fineness modulus of 2.77 that we have just calculated, this indicates that average size of particles is between 300 micron to 600 micron sieve, and more precisely close to the 600 micron. Because you know the sieves are 80 mm, 40 mm, but here we will giving the number from the lowest one, finest one. Means the 150 micron will be given number 1, 300 micron will be given number 2, 600 micron sieve will be given number 3, 1.18 mm sieve will be given number 4, that way. So here we got the number as 2.77. From this 2.77 means something between second and third. So second sieve from the bottom is 300 micron and the third is 600 micron. Means our aggregate is lying something between that. Average size of the particle is between 300 micron to 600 micron, and this number 2.77 is more close to the 3. So that way it is more close to the 600 micron size. So this aggregate is having basically average size which is more close to the 600 micron. The value of fineness modulus is higher for coarser aggregates and lower for finer aggregates. The range of fineness modulus for commonly used aggregates you can see here. For fine aggregates, the fineness modulus ranges from 2 to 3.5. Coarse aggregate range from 5.5 to 8. And if you take the case of all-in aggregate, which is having all sizes basically, the range is 3.5 to 6.5. The range of fineness modulus for various categories of sand you can see. Fine sand, the range is from 2 to 2.6. Medium sand 2.6 to 2.9. Coarse sand 2.9 to 3.5. This is the range for fineness modulus for the various categories of sand. Now generally the sand with fineness modulus ranging between 2.2 to 3.2 is considered suitable for making concrete. The fineness modulus is useful in grading the given aggregate for designing the mix economically for the given strength and workability with the minimum amount of cement base. So this is its importance or use, you can say. The aggregates with higher fineness modulus produce harsh concrete, and with the lower fineness modulus will give you uneconomical mix. The fineness modulus is also used to provide a rough check on the batch to batch variation in the grading of aggregates obtained from the same source. Now let us move to grading. How grading is done, what is grading basically, and how the sieve analysis results are used for grading. So the particle size distribution in a given sample of aggregate is termed as grading of aggregate. Means if you distribute the particles of different sizes, then Simply this will be called as grading of aggregate. The grading of aggregate can be conveniently defined with the help of grading curve. The grading curve is a curve showing the variation of cumulative percentage of passing on y-axis you will be taking, and on x-axis you will be taking the different size of the sieves. And different sieve size, because it varies from micron size to some basically 80 mm, 40 mm. So this variation is so large that if you draw it on a simple scale, that will not be possible. So that is taken on the log scale. So this curve is prepared on a semi-log scale. On x-axis, the log scale, we take the sieve sizes. The grading curve for the data obtained in table 2 from the sieve analysis result is shown in the figure. Next, here you see this figure. Here on x-axis you see the different sieve sizes from 150 micron to 10 mm. So you see that size of variation is too much. So that way this can be drawn on the log scale. On y-axis you see the percentage passing. So these are the percentage, and this is taken on the normal scale. And you see the curve starting from that 0% to the 100%, and different points A, B, C, D, E, F on this curve. I'll explain these, what are the different portions of the curve. So in this curve, the steep slope of the grading curve, which is from A to B, means between the 300 micron to 600 micron size, indicates the greater portion of these size particles in the sample. So let us see this, the portion between A to B. So here it is having the very steep slope. Steep slope means within a small range of sieve size, the larger percentage passing is covered basically. You see that 300 micron to 600 micron, roughly something 18% to, if you go to the B, then something 50%. So within this 300 micron size to the 600 micron size, the percentage size passing through the sieve is varying from something 18% to 50%. So within that, a small difference of the sieve size. So that way means you can say here that 18% of the sample to that 50% of the sample is having this size. So this is the predominant size in the sample of aggregate. Now the uniform slope of the grading curve, which in this case is from B to D, that is between 600 micron to 2.36 mm, indicates the continuous grading. That is, particles of all sizes between 600 micron to 2.36 mm size are present in the sample. So let us see this B to D on the curve. If you go from B to D here, that now the slope is not steep, and because of that the range of the sieve size now increasing. Now it is taking from 600 micron to 2.36 mm. And with this large range of that sieve size, if you look at that percentage passing, 50% to almost something 85% or 86% basically. So that way means it is having large size, different sizes, you can say different size of particles in this range. Now let us move to the flat slope of the grading curve, which is from D to E, means between the sieve size of 2.36 mm to 4.75 mm, indicates lesser or negligible contribution of the particles of that size. Because in this size between D to E, if you look at that figure, D to E percentage passing is very small now. Something between 88 to something 98 on something only about 10%, and sieve size here is 2.36 mm to 4.75 mm, and only something 8 to 10% of the sample is only retained between these sieve sizes. Means now this size of aggregate is very less in this sample. And if you look here from E to F, now the percentage is very less, and sieve size vary from 4.75 mm to 10 mm. Means here you see that almost this type of or this size of aggregate is almost missing in the sample. So this is the meaning of this curve, basically how this curve is read and what is the meaning of this curve basically. The horizontal portion of the grading curve represent gap grading. Means in the curve, if some portion is horizontal, it indicates that that particular size of aggregate is missing. Means then it is called gap grading. For example, the curve in the figure represents the gap graded aggregate in which the particle size 600 micron to 2.36 mm are almost absent. A single numerical value or a mathematical formula cannot specify the good grading of aggregate. In fact, one should go for actual trial and error procedure in order to obtain reliable and satisfactory grading. You see here gap graded aggregate. Between B to D, the curve is flat. Means this particular size from 600 micron to 2.36 mm, this particular size of aggregate is missing in the sample. The good grading of aggregate basically implies that the aggregate sample is having required proportion of all standard fractions of the aggregate, so that sample contains minimum voids and provides least surface area. This will require minimum cement paste to fill these voids. That is, requirement of cement and water will be reduced and will lead to greater strength, better economy and less shrinkage and more durability of the concrete. So this is the advantage. Also, proper care should be taken in selecting the grading so as to avoid segregation. Generally, the workability of a concrete is governed more by grading of fine aggregate rather than the coarse aggregate. So in this discussion, what we covered, first we talked about flakiness index, then elongation index, then I discussed about the sieve analysis, how it is done, what is its importance, then how fineness modulus is calculated and what is its importance for concreting work, then how grading of aggregate is done, that was discussed. So thank you for watching.